Hello and welcome to this module, module 15. In this module, we will be seeing about the NEOS 2 processor, which is a soft processor. So, in this module, students will understand the components of the NEOS 2 processor, what are the advantages of using the NEOS 2 processor in design, and also about various processor variations and how you can actually program the NEOS 2 processor and what options are available. So the NEOS 2 processor is actually a soft IP core. In other words, it's a soft core processor and it's a fully functional processor in software, and it's written in a hardware descriptive language that can be synthesized and programmed onto a programmable hardware such as an FPGA. So it also is a RISC, which is a reduced instruction set computer, and it can be configured for 3 different configurations, namely with no pipelining, with 5 or 6 stage pipelining. It is a complete 32-bit processor, so therefore it has a 32-bit instruction set. The data path is a 32-bit, and the address spaces also are 32 bits. So it has 32-bit general purpose registers, just like your AVR, which we saw in the last module. We also have interrupts, and also has a bunch of peripherals and interfaces to off-chip memories and other peripherals. So you can actually program this particular soft IP core using assembly language as well as C programming language, and so Altera provides the software development environment based on the GNU C, C++ toolchain and an Eclipse IDE in order to program this particular processor. So as we had earlier said, so you can configure this processor and download it into an FPGA. So you can see by using one of those lower end Cyclone series FPGAs from Altera, you could actually fit your NEOS processor inside the FPGA, and you can also have some other elements or LUTs or configuration blocks available to develop custom hardware. So if you're actually dealing with a larger FPGA like the Stratix 2, so here you can see that we can now fit multiple NEOS processors, and we could actually do much more multiprocessing systems on the FPGA using the NEOS 2. So the NEOS 2 processor core itself, as we mentioned, is a RISC processor. It's fully synchronized interface in the sense that it has clock circuits and clock distribution circuits, PLLs, etc. It can be natively programmed using Verilog as well as VHDL hardware descriptive languages. You could configure them as no pipelining or 5 or 6 stage pipelining, and the different stages of the pipelining include fetch, decode, execute, memory decoding, and write back operations. So it also implements static branch prediction, and also has an option to do customizable instruction logic. You could actually create your own 5 new instructions for your NEOS 2 processor. It also has tightly coupled memories, So you can see that it's basically a fast buffer which can hold a critical section of a code or a critical loop or anything that needs to be implemented faster, like a fast interrupt handler. And so because it actually gives you a constant access time. So you can also see that it has two caches, instruction cache and data cache, and each one of them actually have the corresponding tightly coupled memory. So you have a tightly coupled instruction memory and a tightly coupled data memory. So here you can see that is our ALU, and this is our general purpose register from R0 to R31. We have the other support circuitries, and this is the one that we talked about, is the custom instruction logic, which allows us to create new instructions by programming new hardware support for your ALU. So there is a built-in tool that allows you to configure the type of processor that you need based on your application. So here you can see that it offers three different modes or cores. So we have the non-pipelined version, and we have the 5-stage and the 6-stage pipeline. So here you can see we have a basic processor, and over here we have a basic ALU, but with instruction caches, branch prediction, hardware multiply, and hardware divide. And in the bigger version, you have also the barrel shifter, the data cache, and the dynamic branch prediction that is also included. So here you can see that we can actually run it as fast as 57 dry stone million instructions per second. Here is 37 million instructions per second, and this is 8 million instructions per second. And we can also see the number of logic elements that is needed to implement these three variations of your NIOS. So as you can see, the E version is a single stage, no pipeline. The S version has a 5-stage, and the F version has a 6-stage pipelining. So here are some of the execution times of certain instructions. As you can see, most of the instructions, common instructions, takes 1 cycle. And branches, if branch is correctly taken, then it is 2, and if it is not taken, then it is 1. So again, you have some misprediction in branches, which takes 4 because your pipeline needs to be flushed. And then there are other special instructions like jump and the call. Those instructions actually take 4 cycles. So the way you can configure this is by using an SOPC builder, which is basically called as a QSys system. The QSys system allows you to configure the processor and customize it. We can also develop our custom logic. So here you can see we have an NIOS ALU, which has a simple version, has the addition, subtraction, shift operations, and logic operations. But let's say for some reason you want to create your own logic, so you can also create your own logic, and we can actually include up to 5 new instructions as part of your design. And we can also see that we can also generate C and assembly macros for your custom logic and include it as part of your design. So the QSys system also provides you with the profiler tool to estimate the delay or latencies of instructions or execution. So there are 2 ways in which you can program the NIOS 2 processor. Number 1 is by assembly. So here you can see that there is an example assembly code that is given. So here you can see that the instructions are a little bit different. So here these things are actually called as assembler directives. Label, these are all labels, and similarly these words, dot words, anything that starts with a dot is actually called as an assembly directive. So here again you have labels, and in this example we have two arrays or two vectors, vector A and vector B, and this particular algorithm performs a dot product of these two vectors. And we can also program the NEOS2 processor in C. So here you can see there is a cross compiler provided along with your QSys system that is used to program the NEOS2 processor in C. So on completion of this module, the student should be able to understand the components of your NEOS2 processor and the synthesis and the tools for different NEOS process variation, and the examples of how to write assembly program are actually given in CpE200D. Thank you.